This is Geometry Lesson 3.4, Algebra Properties that are used in geometry. Our big idea says the properties of operations of real numbers that you used in arithmetic and algebra can be applied in geometry. So in this section, we are just going to be looking at some properties that you are very accustomed to using from algebra, and we're going to take a look at how they apply specifically to geometry. So we're just going to be looking at these properties and discussing them and using them to prove why we're allowed to do certain things, and then looking back and trying to identify the properties themselves. So we've got a couple properties on the front that deal with equality, and then on the back we're going to look at inequality. So let's jump right in. The first couple, very, very common ones that we don't even necessarily talk about, they're just assumed very often. So our postulates of equality. So for any real numbers, A, B, and C, don't be confused by kind of that math jargon. They're just representing three different numbers with A, B, and C. We have the reflexive property of equality where A equals A. That's one that we really don't talk about very much because it's just saying that any number can represent itself. And so, you know, it's something we already know, it's something we assume. Where this comes into play in geometry is if we have a segment, say ST, and we know the length of that segment is whatever it is, 5. If that segment is now used as the side of a triangle, okay, ST still equals ST. Even though now it's part of a triangle, it's a side, it's something else. If it was used to create an angle, it's still equal to 5. ST is always going to equal ST. So that's what the reflexive property basically touches on. The symmetric property of equality says if A equals B, then we know B equals A. In algebra, we would look at that as saying you can write something as 3 equals x, or you can say x equals 3, and those mean the same thing. Okay, that's the symmetric property of equality. And then the transitive property, a little more useful. If A equals B and B equals C, so we're using all three letters here, then we know A equals C. So for instance, if I know x equals 4y and I know 4y equals 16, I can assume that x equals 16. That's what the transitive property says. X is equal to 4y and 4y is equal to 16. So both x and 16, since they're equal to 4y, that means they're equal to each other. That's your transitive property. All right, and then ones that we're going to use a ton of here in the coming chapters is your properties of equality and operations. So things now we're going to actually start using to solve stuff. So the addition property of equality is one that we use all the time when solving an equation. You may not be conscious of it, but you're using it. So if A equals B, then you're allowed to say that A plus C equals B plus C. Let's put some numbers in there. If x equals 4, then A plus C equals B plus C. If you look at these two parts, they both have the A and the B on the left and the right. They've just added a plus C on both sides. So I can say x plus 2 is going to equal 4 plus 2. I can add 2 to both sides. Seems kind of silly just on its own, but when we go to solve an equation and we have x minus 2 equals 8, how do we solve it? We are adding 2 to both sides of the equation, and x equals 10. This property right here is the addition property of equality. It says we're allowed to add anything we want to both sides of the equation. It still maintains its equality, and that can help us solve equations in algebra, and we're going to take a look at how that can help us in geometry. And then the multiplication property of equality, we use this all the time as well. If A equals B, then I can multiply both sides of the equation by C, and they are still equal. Now, when we look at these, we sometimes subtract on both sides, we sometimes divide on both sides. those would still fall into these. So if you're considering subtracting on both sides, so if it says y plus 7 equals 20, and you say, well, I'm going to subtract 7 on both sides, is that the subtraction property of equality? Yeah, in a way, but we can also classify that as addition because we can say that we are doing plus -7, plus -7. That's the same as subtracting 7, and we get 13. So we're just going to call this the addition property and the multiplication property for now. Dividing would be the same as multiplying by 1 over something. So if we had 15x equals 30, we know that we normally would just divide by 15. So you might want to call that the division property. Well, that's the same as multiplying by 1 over 15. So dividing by 15 and multiplying by 1 over 15, that's the same thing. These cancel. This is the same as 30 divided by 15, and it's 2. So again, we look at this as division, but it can be expressed as multiplication. So instead of having 4 properties right now, we're just going to talk about addition and multiplication. So even if it looks like division, we're going to call it multiplication. Even if it looks like subtraction, we're going to call it addition. And so the example here, as we run through this, we are going to show how these postulates are being used. Here's your given. 50x minus 8 equals 120. We know how to solve this. We would add 8 to both sides, and then we would divide by 50. And so that's what's going on here. You can see they added 8 to both sides. We got 128. They divided by 50, and you got 2.56. Okay, but we are going to now link up these properties to prove why we're allowed to solve this the way that we did. So on the right, the initial equation was given to us. And then how did we get from here to here? We used the addition property of equality, which again is stated right here. If A equals B, then I can add C to both sides. So if this equals this, I can add 8 to both sides. And so in this specific situation where they're adding C to both A and B, that's 8. We're adding 8 to both sides. So it clears out the minus 8, and this becomes 128. And then like I just talked about over here, we're looking at this as division. Okay, but this is also could be considered the multiplication property of equality. If two sides are equal, you can multiply both sides by the same thing. And so we multiplied by 1 over 50, which looks like dividing by 50. So we use the addition property of equality for step 1, the multiplication property of equality for step 2, and then they rewrote the fraction as a decimal here. That's not a property. But just an example of how we used this in algebra. Now let's take a look. How can we use this in geometry? So down here at the bottom, we've got this picture. We've got a bunch of different angles here. If you notice, we've got these markings in the picture. That means that those angles are equal to each other. So AVB equals CVD. And you can see that right here. It's given to you from the picture. So if two sides are equal, going back to this property right here, if two sides are equal, I can add the same thing to both sides, and they're still going to be equal. And so I've got those two angles, and then I've also got this one in here, BVC. And so I can add that angle to both of them since they're equal, and the result is still going to be equal. So since AVB equals CVD, I can take AVB and add BVC to it. So that would be all of this. I'm going to add them together, make one big angle, AVB plus BVC. That has to equal CVD plus BVC. So this little angle and BVC added to it, they have to be equal to each other because these two were equal to start with, and I'm adding the same thing to both of them. So therefore, they're still going to be equal to each other. And so this is the addition property of equality. I'm allowed to add the same thing to both sides. I've added the measure of BVC to both sides. And then from there, I can use my angle addition postulate. This plus this equals the whole thing. So AVB plus BVC, this one plus this one, is going to equal this big angle right here, AVC. That's where this comes from. And CVD, this little one, plus BVC, if I put those together, they become this one big angle, BVD. And so I'm allowed to conclude now that AVC is going to be equal to this one, BVD. Using my addition property of equality and my angle addition property, I know that that angle equals this angle because I started with these two equal, and these combinations that I'm now comparing at the end are just our small little equal angles being added with the same angle. So our addition property shows us that those angles are equal. Okay, more on that later. If you flip to the back, we're going to kind of perform the same operations, but with inequalities. So just like in algebra, we learned how to solve an equation, and then we applied it to solving inequalities, and it was very similar with some slight differences on when we flipped the inequality, and we're still going to be looking at that. All right, so for any real numbers a, b, and c, the transitive property of inequality says if a is less than b and b is less than c, then I know a is less than c. So if x is less than 5 and 5 is less than y, I know that x is less than y. So whatever this number is, it's less than 5. And 5 is always less than this. So if x is less than 5 and 5 is less than this, I automatically know x is less than y. That's the transitive property of inequality. The addition property, if you've got an inequality, this is less than this, I can add c to both sides. That's the same as the one we use for equality. If we're trying to solve an inequality, we can add to both sides. So if I had 3x minus 2 is less than whatever, 12, I can add 2 to both sides, and 3x is less than 14. This right here, being able to add to both sides to solve an inequality, that's the addition property of inequality. Multiplication property of inequality. Now, when we go back to just regular algebra, we know we're allowed to multiply both sides of an inequality to solve it. But when we multiplied by a negative, we said multiply or divide by a negative. We had to flip the less than sign. Okay, and that's what you're going to see right here. So this just looks confusing when you read it, but that's what they're showing you. So you have the initial inequality if a is less than b. If c is greater than 0, so if I have a positive number, I can multiply both sides, and it still says less than. Okay, so if, let's see, if I have x over 4 equals 10, or not equals, less is less than 10. I can multiply both sides here, and we know that clears this out, and it maintains that this is still less than. This is still a true statement. That's all this is saying. As long as c is greater than 0, this number that you're multiplying both sides by, you can multiply and it maintains its inequality. But part 2, the special part, and we've talked about this through algebra, is that when c is less than 0, so we're starting with the same thing, but if c is less than 0, so it's a negative number, if I multiply both sides by a negative number, this now has to flip. So if I had x over negative 5 equals whatever, 20, if I multiply both sides and not equals, less than, sorry. If I multiply both sides by negative 5, this clears out. I have x, this has to flip, all right, and I get negative 100. So the key is if you multiply both sides by a negative, and that would include division, multiplying and dividing can be expressed similarly, I have to flip the inequality. So we've covered that in algebra before and reviewed that again this year. But how does that now apply to geometry? So we'll look down here at this situation that we've got right here. So we could read through all this. Sometimes that's confusing. Let's just look at the picture. both of these have this angle Z. Okay, these are two different pictures. But whatever this is, say it's 40 degrees, this is 40 degrees. They're both Z. And then they have these other angles that are attached to them, adjacent to them, right? And so X looks to be smaller than Y. And if that's given to you, okay, we're allowed to assume that. But if it's not given to you, you can't. So at the figure at the right, you've got angle DBC, which is X, and the measure of HEF is Y. And then they tell you that both of these are equal to Z. If this is given to you, if X is less than Y, which it certainly looks like in the picture, then by the addition property of inequality, I am allowed to assume this. So I have X plus Z less than Y plus Z. So why am I allowed to assume that? So I've got Z on both sides being added to X is less than Y. So my starting point was right here. I know that this is less than Y. So I can add Z to both sides and it's still going to say less than. So X was less than Y. Now that I've added Z to both sides, it doesn't change the fact that this is still less than this because I've added the same thing to both sides. X was less than Y. I add this angle Z to both of them. This side is still less than. So I'm now allowed to assume that angle ABC is less than angle GEF. So this whole angle is less than this whole angle because I knew X was less than Y, and all I've done to create these bigger angles is add Z to both of them. So that's not going to change the fact that this is still less than this. All right, and then the last part, going from equations to inequalities. So the equation to inequality property, going from an equation to an inequality. A and B are positive numbers. If I know A plus B equals C, so some number plus some number equals C, I'm allowed to assume that C is bigger than A and C is bigger than B. Think about why that makes sense. I'm adding two numbers together to create C. So these must be smaller numbers, and when they're combined, they create one bigger number. So individually, this bigger number has to be bigger than A and has to be bigger than B because I have to add these together just to get there. If you look down here, this equation to inequality property sometimes is stated as the whole is greater than any of its parts. Again, seems pretty obvious. The whole thing is bigger than the two parts that were put together to create it. Now, for geometry, for example, in the figure at the right, we know that the length of zx is bigger than the length of zy, and it's also bigger than the length of yx. Those two, based on your addition postulate, have to be added together to create the bigger segment. So therefore, the full segment, xz, has to be bigger than xy, and xz has to be bigger than yz. Because we know that if I add the two little pieces together, I get the big one. Therefore, the big one is bigger than the smaller ones. Again, some of these seem like, well, duh, why do we have to state that? I get that. But as we start trying to prove things, we have to have this information to back it up. And then the substitution property, the last one we're going to look at here today. If A equals B, then A can be substituted for B in any expression. And we use this all the time. If you look down here, suppose you know that 2x plus y equals 18. I'm just going to rewrite it on the side so that it makes a little more sense. If you know that y equals 3x also, we've looked at it like this, y equals 3x. So I can come in here and change y to 3x. So this becomes 2x plus, instead of y, since y equals 3x, I can plug the 3x in right there, 18. So you can substitute 3x for y and get this. So that is your substitution property, and we can do that as well with a geometric figure.